Assalamu alaikum students, this is your course Power System Analysis, and we're going to start our lecture number 2 for this course, which is basically per unit system of calculations. Since you are not familiar with the basic understanding of the power system and the equipment related which is involved in the power system, like motors, generators, transformers, so you might be familiar with the basic calculations that is involved in the understanding of these equipment and the problems that you solve while developing the theories concerning power system. And so it is a method. Per unit system is a method which is considerably advantageous to use a system of calculation. How you call it advantageous? Because as compared to your conventional approach that you use in the transformer, like the referring thing that you refer its calculations, there are certain different values on one side of the secondary and primary sides. So there is a hectic calculation which can be overcome by the use of per unit system, and we're going to see how we have the advantage of using a different system of calculation as compared to our previous approach. Well, basically this system involves the selection of an arbitrary base value depending on the circuit for a quantity like voltage or current. So we normally select a voltage value or the current value as a base value, and then any actual value of that quantity, when we divide it by its base value, will give us its per unit value. So how we define per unit value is the per unit value of any quantity is defined as the ratio of the quantity to its base value expressed as decimal. So this is the formula. The per unit value is equal to actual value over base value. Well, this actual value can be of any parameter, whether it is voltage, current, power, or impedance. So there are basically 4 basic electrical parameters which are involved in the system calculations, which are the kilovolt ampere or megavolt ampere, kVA or MVA normally, and the second parameter is kilovolt, which is the voltage. So first thing was power, second is the voltage, which is normally in kilovolt, then we have current, and the fourth one is the impedance, which is denoted by Z, which is basically the combination of resistance and reactance, and you normally write it as R plus JX. So these are the 4 basic electrical parameters which is normally used in the system calculations, and ideally normally we have VA as volt ampere or voltage, and current and impedance as the standard parameters, the basic parameters. But in practical systems, kVA and kilovolt are mainly used. There are large terminologies. The voltage is in kilovolt and power is in kVA. So these are the mainly terminologies that will be used in practical calculations, and we should retain in subsequent derivations. So how we solve the per unit system? The basic parameters are so related that any two of them may be expressed in terms of the other two. So it would thus be necessary to select the base value for only 2 of these variables. Whether we consider the voltage or power or current or impedance, we take any 2 of them as the base values, and the base values of the remaining 2 will be derived from them, and we're going to see the derivation. But in the normal practice power system calculations, we normally select kVA and kilovolt as the base values of any machine and any equipment we have, whether it is transformer or transmission line. For any kind of equipment of the machine, we standardly we take as kVA and kilovolt as the system base, and then we derive the relationships for base current and impedance in terms of these parameters. So let's see if kVA is the base kilovolt ampere and kVB is showing that it is the base value. So kVA is base kilovolt ampere and kV is the base voltage. So keeping these 2 parameters as base values, how are we going to derive the current and impedance from them? Whether we are using a different system of calculation, it is per unit, but the standard definitions will remain the same. So base current is basically the ratio of power over voltage. So it is kVA over kV. So taking the base values of power and voltage will give us the base value of current, which is base current in ampere, IB, and similarly the base impedance in ohms. Normally the ohm impedance is equal to V over I. So here we will take base impedance is equal to base voltage over base current. And here you can see there is a parameter of 1000. This division of 1000 is just to convert this voltage into kV, because we have kV as the base value instead of simple voltage. So taking it in kilovolt will require this multiplication of 1000 factor. So we have taken voltage in kilovolt and current in IB simple amperes, then multiply by 1000 will give us the value of Z base. And if we replace the value of IB from this equation, replace it here, and you can see here this is kVA base over kilovolt. So here you can have kilovolt will go upward, and this is the complete formula, that the base impedance is equal to square of the voltage, kilovolt square, multiplied by 1000 divided by kVA base. So you will use this formula to calculate the base impedance, which will be derived from the voltage and power as base values. So this is the base value. How we're going to get the per unit value of the actual impedance ZB? So if ZA, let's say, is the actual impedance, then we have Z per unit is equal to actual value over base value. So ZA is the actual value and ZB is the base value, which is calculated using this formula. It is equal to ZA multiplied by this whole formula is replaced here, and because this ZB is in denominator, so we have just replace it like this. And if Z actual is equal to R plus JX, because the impedance has the resistance and reactance parameters both in this equation, then we can say that the per unit resistance is equal to its actual value divided by the base impedance, and similarly per unit reactance is equal to XA divided by Z base. So whatever the actual value of resistance and reactance in given in the ZA value, you just have to divide it with the base impedance and you will get the per unit value. Similarly, per unit voltage and per unit current will be similarly calculated by dividing the actual values with the base values. The normal relationship between electrical quantities hold true in per unit form also. For example, per unit current, here it is equal to V per unit over Z per unit. So wherever applicable Ohm's law will be applied, the power, voltage, impedance, all the general relations will be similarly applicable in per unit form. So there is no confusion or any new thing that you have to apply. We just have to take a standard base value, and keeping it as a standard, we just have to derive the remaining parameters and then we convert it into per unit. One parameter is left, which is inductance. We have calculated the resistance and reactance in per unit. So if we have to calculate the inductance of inductance value in per unit, then we know the formula. Basically, inductive reactance XL is equal to omega L, from which L is equal to XL over omega. This is the general equation. Where we know that here L per unit will be equal to basically X per unit divided by omega per unit. So we just have to take both the values in per unit, where reactance per unit is basically equal to XA over ZB. So a reactance value divided by the base impedance, and omega per unit is basically equal to omega A over omega B, where basically omega A is the actual speed, which is equal to 2 pi f, corresponding to a frequency of f cycles per second, and omega B is the base speed, which may be arbitrarily selected. The value of base, this is the actual base speed that we have, omega B. We have two options to select its value, whether we take it is equal to omega A, which is equal to 2 pi f, where f is the natural frequency corresponding to synchronous speed, or it may be chosen as simply equal to 1.0 radian per second. So there are two options to select the value of omega B, and we can take both the values and we will see. And from this equation you can see that if we take omega B is equal to 2 pi f, which is equal to omega A basically, then as both these values will be equal, so we will just have the omega per unit value equal to 1.0 radian per second. And in the other case, if we take omega b is equal to 1 radian per second, so if we put 1 in this denominator, then we just have per unit value of omega is equal to omega a. So we'll see in calculation both these formulas. We will replace omega b in both forms and see the difference.